Have you ever stopped to think about the difference between the space on something versus the space inside it? You know, it seems super basic, but the concepts of area and volume, they are absolutely fundamental to how we understand the world. So let's dive right in. We're going to go on a little journey, starting in the flat, two-dimensional world of surfaces and building our way up into the solid, three-dimensional world of space.
Okay, let's kick things off with a couple of real-world questions. Say you're going to paint your house. Are you dealing with its area or its volume? And what if you're filling up a swimming pool for the summer? The answers to these questions, well, they get right to the heart of what we're talking about today.
So, here's our game plan. First, we'll tackle the idea of covering versus filling. Then, we'll explore the flat world of area. From there, we'll build up into 3D volume, uncover a really cool secret that connects them, and even figure out how to handle some, well, weird shapes. And finally, we'll wrap up with why all this dimensional thinking really matters.
All right, first things first, we have to understand the core conflict here. Is our goal to cover something, or is it to fill it?
This breaks it down perfectly. Think of surface area as the outside wrapper of an object. It's what you'd paint on a house or the wrapping paper you'd use for a gift, and we measure it in square units. Now, volume, that's the space inside. It's about how much stuff you can fit into something, and for that, we use cubic units. See the difference? One's for covering, the other's for filling.
Okay, so to really get a grip on this, we've got to start at the beginning. We need to ground ourselves in two dimensions, in the flat world of area.
So what is area? The most important thing to remember is that it's a two-dimensional measurement. It's all about the space a totally flat shape, like a square on a piece of paper, takes up. And you always find it by multiplying just two dimensions, like its length and its width.
And when you look at these common formulas, you see a pattern, right? For a rectangle, it's length times width. For a circle, it's basically the radius times itself. The common thread here is that you're always working with just two dimensions. And that's exactly why the answer is always in square units, with that little 2 up top.
All right, now for the fun part. This is where it gets really interesting. We're going to take everything we just learned about the flat world and use it to literally build our way into the third dimension.
So, volume, by definition, brings us into the 3D world. It's the amount of space a solid object actually occupies. And to figure that out, we need to multiply 3 dimensions: a length, a width, and now a height. That's why we get cubic units.
To really see how this works, let's start with something super simple, a flat circle. We already know how to find its area, but what happens if we start giving it some height?
And boom, this is where the connection becomes crystal clear. Imagine that circle is a single paper-thin disk, like a coin. Now just start stacking more and more identical coins on top of it. Building a tower? What have you made? A cylinder. And its volume? Well, it's just the area of that very first coin, the base, multiplied by the height of your stack. It's that simple.
That stacking idea is a fantastic way to visualize it, but it hints at a deeper, more powerful connection between area and volume. Let's call it the secret of slicing.
First, let's get a key term down. A cross-section. It's actually a really simple idea. Imagine you have a loaf of bread. If you cut a slice from anywhere in the middle, the 2D shape of that slice, that's its cross-section.
So let's go back to our cylinder. If you slice it horizontally, it doesn't matter where you cut, the cross-section is always the exact same circle. Its area is constant. But now look at a cone. Every horizontal slice is still a circle, but its area is constantly changing, right? It gets smaller and smaller as you move up toward the tip, and that difference is crucial.
And this is the secret sauce. The volume of any solid object is really just the sum of the areas of all of its cross-sectional slices. You're basically adding up an infinite number of flat, 2D areas to create a 3D volume. It's an incredibly powerful idea when you think about it.
Okay, so this is all well and good for perfect cylinders and cones. But what about the real world? What happens when things get a little messy or skewed or just plain weird looking?
Let's try a quick thought experiment. Imagine you have a perfectly neat stack of coins. Now, you kind of push it over so it becomes a messy, skewed stack. Which one takes up more space? Does the skewed stack have more volume, less, or is it exactly the same? What do you think?
Well, the answer is, they have the exact same volume. And this is explained by a really clever idea called Cavalieri's principle. It basically says that if two objects have the same height, and here's the key part, the same cross-sectional area at every single level, then their volumes have to be identical. Since each coin in our stack is the same,
The area at every level is the same, whether the stack is neat or totally skewed. Pretty cool, huh?
Okay, so Cavallari's principle is great for skewed things. But what about something that doesn't have consistent cross-sections at all? I'm talking about something like a lumpy rock. You can't exactly calculate the area of its slices, so what do you do then?
For a problem like that, we turn to a brilliantly simple, old-school method: water displacement. It's so easy. You just fill a container with water and mark the level. Then, you completely submerge your rock, or whatever it is. Naturally, the water level rises because the rock has pushed, or displaced, a bunch of water out of the way. And get this, the volume of that water that was pushed up, that is exactly the volume of your object. It works for anything that won't get ruined by water.
Wow, okay, so after that whole journey from flat shapes to lumpy rocks, let's bring it all back home and put a bow on it with one final, clear comparison. And this table just lays it all out nice and simple. Area is two-dimensional, it's for covering a surface, and it's measured in square units. Think how much carpet you need for a floor. Volume is three-dimensional, it's for filling a space, and it's measured in cubic units. Think how much water you need for that pool. It really is the difference between a flat blueprint and the actual solid building. So, we've seen how area is literally the building block of volume. But here's a final thought to chew on. As an object gets bigger or smaller, how does its surface area, its wrapper, change in relation to its volume, the space inside? That relationship is actually one of the most important concepts in all of science and engineering, and it's a really fascinating question to explore next.